Okay, well, in any case, today's material is pretty important. So I hope it excites you, gets you out of your low energy state. So we are in section 3.5.3, and we're talking about, remember, exponential functions. And we finished off last time saying that there was this base, right? There was a base that you can use for the exponential function, and it's unusual. It's this number e, which is defined as the sum of 1 over n factorial as n goes from 0 to infinity. So I don't think I've introduced this notation before, but it's a good time to do it. So what this letter is sigma in Greek, and it's a capital sigma, and it stands, in this case, it stands for sum. So we use this as a sum. So you read this thing as the sum as n ranges from 0 to infinity of this thing. Okay, so you're summing this term as n ranges from 0 to infinity. Okay, so that is, what this would be is you first let n equal to 0, get 1 over 0 factorial. Then let n equal 1, that term becomes 1 over 0 factorial, and then 1 over 1 factorial, right? And then 1 over 2 factorial, plus 1 over 3 factorial, and then so on and so forth. And you have this infinite sum. Okay, what an infinite sum means at this point is not clear. Okay, but you'll learn about it in calculus 2, in fact. But you can kind of guess it's going to involve some sort of limiting process, right? You know what a finite sum is, right? You would be able to sum these first few terms. This is 1 over 1, plus 1 over 1, plus 1 over 2, plus 1 over 6, right? You'd be able to sum these first few terms. And then what you do is you say, okay, we'll look at what happens as you keep on summing more and more terms and see what happens in the limit, what that tends to in the limit. And it tends to some number, 2.1828, et cetera, et cetera. Okay. So, I'm sorry, what am I saying? 2.71828. 2.71828. Okay, and we said that this was the best, this was in some sense the most natural base to use for the exponential function. So the natural exponential function is e to the x. Okay, we use that as the base. And there's a book, there's a book that I think I probably saw it in graduate school that starts off by saying, this is the most important function in mathematics. There are people who think in this way, and that maybe that I think that's probably true. In fact, from my perspective, that is true. So the most important function, the most important function in mathematics. So what's so unusual about it? What's special about it? To understand that, we have to introduce a kind of variation on the idea of average rate of change. So remember average rate of change, right? You have some interval, you have some function, right? So you have some time interval, say like a plus h, right? So here's your time. Maybe you think of it as time. You have some time interval, and you're thinking of the average rate of change of the function over that. So average rate of your function over this interval And you guys remember, I think, how to do it, right? You would take, what's the average rate of change? Somebody tell me. Nobody remembers? It's okay. Not at all? Yes, f of a plus h minus f of a over a plus h minus a, right? Right, or if we call that b, it would be f of b minus f of a over b minus a, right? So this is the change in f over the change in x, change in t, excuse me, over that time period, right? Okay, so that is, and we notice that that is the slope, geometrically, that is the slope of the line through these 2 points here. Okay. So there's something called instantaneous rate of change. It's what you get when you let the interval shrink down to infinitely small length. So you let h go down to 0. Okay. So let me just give you an example here. If we have the function f of x equals x squared, right? And we look at the instantaneous rate of change. Well, let's look at the average rate of change over 1 plus h. Okay. How do we get that? Well, that's going to be f of 1 plus h minus f of 1 over 1 plus h minus 1. Right? Everybody okay with that? Right? So you take f, you take the function at the second point minus the function at the first point over the length of this interval, which is the point on the right minus the point on the left. Right? So this function is a squaring function, so we're going to get 1 plus h squared. I'll let you take 1 minute and write out what that would be, just for algebra practice. Okay, somebody want to tell me what they get? Sure. Here's my 1, 2, 3, 4, 5. 1, 2, 6, 7. So.
I got
2 plus h. Tell me what you did here.
Well, so first I just wrote basically everything out the same, but then I substituted for f of 1, just 1 squared.
Yeah. So you get f of 1 is 1 squared, f of 1 plus h is...
Would be 1 plus h.
1 plus h squared, so you get 1 plus h squared minus 1 squared, and then on the bottom, we've got 1 plus h minus 1, so that's just going to be h, right? So then when we square that thing, right, we get 1 plus 2h plus h squared minus 1 squared over h, right? The ones kill each other off, and we get 2 plus h. You can factor out an h on the top and the bottom. Right. So you get 2 plus h, right? Okay. So that tells you that the rate of change is 2 plus h, right? So if we look at the interval over the interval 1, 2, what's the average rate of change? Stella?
3.
It'd be 3, right? Because the h is the length, right? So it's 2 plus the length, which is 1, which is 3, right? Over 1, say 1.1, what would be the average rate? It's going to be 2 plus the length. What's the length of this interval? Starts at 1, goes to 1.1. What's the length? 0.1, thank you. Right, so you get 2 plus 0.1, right? 2.1. If we're at like 1 comma 1.01, well then what's the average rate of change going to be? Just shout it out. Anybody? Nope. Thank you. 2.01. 2.01. Right. We go 1 comma 1.001. Well, it's going to be 2.001, and so on and so forth. Right. So you see what's happening as the length gets, as this interval gets shorter and shorter. What happens to the average rate of change? What does it get close to? It's going to turn into eventually. It's getting close. These numbers are getting closer and closer to 2, right? So what's that saying? That's saying that if we go from 1 to 2, that the slope of this line is 3, right? If we go from 1 to 1.1, the slope of that line is 2.1. If we go from 1 to 1.01, the slope of that line is 2.01 and then 2.001, et cetera, et cetera. Those lines are getting closer and closer to slope 2. So get close to a slope of 2. Okay. And that thing is what we call the instantaneous rate of change. Okay. So that 2 is the instantaneous rate of change. At t equals 1. Okay. If you want to think of this in terms of cars, okay, if you have a car that's driving it's at a position of, this is the position of the car along a track, right? The position of a car along a track. So at time 0, it's at 0. At time 1, it's at 1. At time 2, it's at position 4. At time 3, it's at position 9. At time 4, it's at position 16. So this car is really speeding up. Okay, right? As time goes on, this car gets pretty fast. Starts speeding up. So what we're doing here is we're calculating the velocity at that point in time. Okay. And the way we're doing it is we're saying, well, the average velocity over 1 second, right? This was the average velocity over 1 second, right? So it was traveling 3 miles per hour, say. Okay. If we look over this interval, the next smaller interval here, that speed over that interval was 2.1 miles per hour. The speed over the next smaller interval was 2.01 miles per hour, 2.001 miles per hour, et cetera, et cetera. So we can say, what we say is that at this time, it was traveling 2 miles an hour. Okay, at time 1, when it crossed this point, it was traveling exactly 2 miles an hour. Okay, so it's like the instantaneous velocity. So, okay. Do people have questions? Maybe I feel like people are not quite getting it. Talk to each other for a minute, and then see if you can formulate a question if you have a question. Okay, did anybody come up with a question? Anybody have a question? Is it clear? Yes? No? Fine. So what I'm trying to get across is that if you have a function, there's a way of, you can look at what we've done before is look at the average rate of change, which is the slope through 2 points above an interval. Okay. But you can also look at something called the instantaneous rate of change. And that turns out to be the slope of what's called the tangent line. So you take a line that just touches the curve. Okay. So the slope of the tangent line is also called the instantaneous rate of change. Okay. And all I wanted you to see was that for this function, the rate of change here is 2. Okay, that's all we did here. We were just looking at the instantaneous, the slope of this tangent line is 2. Okay, so if you have the function f of x equals x squared, and you look at this point, 1, 1, the slope of the tangent line here, so the slope of the tangent line equals 2 here. Okay, that's all that this calculation is. And I'm just going to give you a fact about the parabola. The fact is that if you're looking at the x squared function, then the slope turns out to be the slope at the point x turns out to be 2x. Turns out to be 2x. Okay, so like, you know, if you're at position 1, the slope is 2, right? Yeah, that's back here. So if you're at position 1, if you're at time 1, the slope is 2. If you're at position 2, the slope is 4, right? So if you're at 3, the position is, I'm sorry, if you're at position 3, then the slope is 6, and so on and so forth. Okay. Okay. What's special about the exponential function is this. What's special about the exponential function is that, so the exponential function looks something like this, is that at x, the slope is e to the x. The slope is itself. Okay. So like, this was this business of what we were talking about the other day about like how the money increased so much, right? So like for the x squared function, right? When the value at time 1, so let's think like this: f of x, and then slope. So at time 1, the value is 1 and the slope is 2. Right? At time 2, the value is 4 and the slope is 4. Right? At time 3, the value is 9, the slope is 6. At time 4, the value is 16 and the slope is 8. Okay, but for the exponential function, right? So you have the exponential function, e to the x, and then so the value, and then the slope. Okay, so like if you're at time 1, the value is 1 and the slope is 1. If you're at 2, the value is e squared and the slope is e squared. And if you're at 10, the value is e to the 10th and the slope is e to the 10th. Right? So what it is, it's this really weird car that whatever position you're at, that's your velocity, right? Whatever position you're at, that's actually your velocity, right? So if your car has traveled 10 miles out, then it's going to be traveling 10 miles an hour. If it's moved, by the time it's moved to 100 miles out, it's traveling 100 miles an hour. When it gets to 1,000 miles out, it's 1,000 miles an hour. When it's at 1,000,000 miles out, it's 1,000,000 miles an hour, right? This car, on the other hand, is very, right? When you're at 16, well, you're 8 miles an hour, right? When you're at 100, you're 10 miles an hour, right? When you're at 100, when you're at 100, you're 20 miles an hour, right? And so on and so forth, right? So it's this weird kind of car where the velocity actually equals the value of the function. Okay, that's what's special about the exponential function. Let me give you a different example. So money example. Okay, so money in a bank or like invested in a stock market grows at an exponential rate. It doesn't grow like e to the x. It grows at something like 1.06 to the x. Okay, but it's still an exponential function. Okay, it's still an exponential function. So you can think of it. Let's just pretend this would be crazy, but let's pretend that the money grows at a rate of e to the x. Okay. Then what would that mean? That would mean that if you got your money up to $1,000, let's say the time unit is 1 year. Okay, if you got your money up to $1,000, your money would be growing at a rate of $1,000 a year. If you got your money up to $10,000, your money would be growing at a rate of $10,000 a year, right? If you got it up to $1 million, it would grow at a rate of $1 million a year. Okay, so like, what would that mean in terms of savings? That would mean at the beginning, you just try to get your money as high up as possible, right? Because the higher up you get, the higher velocity you've got, the higher growth rate the higher the velocity of your money is, the higher that the speed that your money is increasing will be. Okay, so like, when I was first starting out as a professor here, I was like, okay, I've got to take advantage of the exponential function. So I'm just going to save as much as possible. My salary was lower then. I was like, I'm just going to save as much as possible and get the money up as high as possible, as quickly as possible. Because once you get to the higher rates, then the velocity is also higher, right? You could think, oh, I don't have to. It doesn't really matter how I do this. I can sort of do this gradually and then add in the money later. No, it's better to get up to the higher rates more quickly. So, like, just sock it away at the beginning as much as possible, even if it's painful, and get up to the place where your where your savings can speed up, because the higher you are up, the faster the money would increase. This is advice I gave to my sister recently when she was talking about saving money. It's like, just sock it away right now because because of how the exponential function works. I don't know if she knew what I meant by that, but at least she trusted me. I think, I hope, I don't know. This is my big sister, so I don't know. Okay. Anyway, so does this give you some sense of what's sort of special about the exponential function? That the instantaneous rate of change equals the function itself. Okay, and it's the only function like that. There is no other function that does that, except for variations of the exponential function. Graphically, what that means, I don't know if this will be more or less appealing to you than the money, but what it means is that slope of the tangent line, at x e to the x is e to the x. So if this is x and this is e to the x, then the slope of the tangent line is e to the x. And what that means is that if we drop this line and we looked at the intercept of this line, the slope is e to the x, the height is e to the x here. So if we step one back, it'll travel e to the x backwards, right? So it'll always be at x minus 1. Right? If I take so if I take like this point here and I look at this guy's slope, then it should intersect one unit before. If this is some t, then the slope of the tangent line should be t minus 1. I mean, the intercept of the tangent line should be t minus 1. Right? So that's what that means geometrically. Okay, all of that was just to tell you what's special about the exponential function. That it is a kind of unusual function. Yeah. Okay. Yeah. So don't worry if you didn't understand the definition of instantaneous velocity. That's okay, right? I'm just trying to give you some. This is all just to give you some sense of what's unusual about the exponential function. Okay. That was actually 5.2, not 5.3. Sorry. This is now 5.3. So 5.3 is about logarithmic functions. Okay. How many of you have seen logarithmic functions before? Some of you? A few of you? Okay, that's all right. So let me recall some stuff about inverse functions, because the logarithmic function is going to be created as an inverse function. Okay, so f and f inverse being inverse functions means that if f of x is y, then x is f inverse of y. Right? Whenever f takes x to y, f inverse will take y to x. Right? That's what these guys being inverses of each other means. Right? Yes. Okay. Another way of saying that is that f inverse of f of x. F inverse of f of x is x, and f inverse of f of f inverse of y is y. Right? That they cancel each other out. Right? If you run it through the function and then run it through the inverse, you get back to where you started. Or you run it through the inverse function and then run it through the function, you get back where you started. Okay, that's what an inverse function means. Another way of writing that is that f composed with f inverse is the identity function. F inverse composed with f is also the identity function, where the identity function is the function that doesn't do anything. Okay, it just returns what you give it. Okay, so this third one is just a rewriting of the second one. Okay. So, and remember that functions have inverses if they pass the horizontal line test, right? If they are one-to-one, if they pass the horizontal line test. So consider exponential functions. F of x equals b to the x for some positive number b. So let's just for the picture's sake assume that b is bigger than 1, so that we have something going like this, just for the sake of the picture. This is a one-to-one function, and so it's got an inverse function, right? Has an inverse. B to the x is 1-to-1, so has an inverse called log base b. Okay, and you know that the graph of it is going to be the reflection, right? So it's going to look something like that. So this is y of x equals b to the x. This is y equals log base b of x. Okay, so let's think a bit. What do we know about this inverse function, log base b of x? So I'm just gonna write these things out. I'm gonna write these first two things out over there. So b of x equals y if and only if x equals log base b of y. You guys see what I'm doing? All I'm doing is taking this one. Our f is b to the x, right? F is b to the x. So b to the x equals y, if and only if x equals f inverse. Well, f inverse is log base b of y. So I'm just substituting, f is b to the x. F inverse is log base b of x. So I'm just writing that this is an inverse, right? Okay, and the second one says that if you take the inverse function and apply it to the original function, then they cancel each other out. Right? If you compose the inverse function with the original function, then they cancel each other out. Right? It also says that if you do it in the opposite order, if you take the original function, compose it with the inverse function, then they cancel each other out. So we're trying to get some sense of what this function is, right? The exponential function, I think, is pretty easy to think about, right? Pretty easy to conceptualize, right? You're just taking something to a power, right? But what's this log function, right? This log function is the inverse of the exponential function. It's a little bit, you know, like a little bit tough to get your head around. This gives you a way of getting your head around it. Okay, this observation here gives you a way of thinking about it. What it says is that, so it says, what does this mean? What does log base b of y mean? Right, what is it? Right, it's the power one must raise b to in order to get y. Right? It's the power you raise b to get y. Okay, b to the log base b of y is y. Okay, that's probably the easiest way to think about it. I mean, you could think about it as the inverse function. I mean, all these ways of thinking are the same. But I think probably the easiest way to have a sort of internal representation of it is like, okay, what does it mean? It's the power that you raise log base b of y. Whenever you see that, you think, what power do I need to raise b to get y? Right? What power do I need to raise b to get y? So for example, if I say log base 10 of 1, log base 10 of 1, right? You could say, well, this is going to be the inverse of something. Okay, think, what power do I need to raise 10 to get 1? But let me do a simpler one first. What power do I raise 10 to get 10? 1, right? If I say log base 10 of 100, what would that be? 2, right? Log base 10 of 1,000, of course, will be 3, right? Log base 10 of 1 will be 0. Log base 10 of 0.1 would be 1. 0.1, remember, is 1/10. Negative 1, right? Because 10 to the negative 1 is 1 over 10. And so on and so forth. Okay, so this gives you some way of thinking about the log function, right? If I'm looking at log base 10 of x, then at time 1, it's 0, right? At time 10, it's 1. At time 100, right, maybe around here, at time 100, it's 2, right? At time 1,000, it's 3, right? Right, and you see that that is the inverse of the, right? At time 2, I'm going to be at 100, time 3, I'm going to be 1,000. Right, that's the inverse of the 10 to the x function. Right, that's the reflection of the 10 to the x function. So where the exponential function grows very quickly, the logarithmic functions grow very slowly. You don't want to invest in a logarithmic bank. Okay. How about log of the square root of 10, base 10? Log base 10, square root of 10. Don't blurt it out. Write down something. What do you get? Somebody other than Janie and Olivia? Or both banned from speaking? So, yeah, you get 1/2, right? Because this thing is 10 to the 1/2, right? And you're asking, what power do I raise 10 to get 10 to the half? Well, it's a half. Right? Okay. So yeah. So this is how the function looks. So one way of rephrasing this is to say that this is sort of an observation. To every exponential statement, corresponds a logarithmic statement. Okay, that's sort of a rephrasal of this observation here. Okay, that to say that b to the log base b of y equals y is the same thing as saying that so sorry. Let me. Actually, that's not right. Sorry. Here it's a rephrasal of this statement. Sorry. Right. To say that b to the x to say that b to the x equals y is the same thing as saying that x is log base b of y. Okay. So like. Each of these statements over here, right? Log base 10 of 1 equals 0. That corresponds to the statement that 10 to the 0 is 1, right? That's exactly what that says, right? This corresponds to 10 to the 1 equals 10, right? This corresponds to 10 to the 2 equals 100, right? This corresponds to 10 to the 3, oops, 10 to the 3 equals 1,000, right? Every exponential statement, 10 to the blah equals something, that tells you about log base 10 of that something equals that exponent. Okay, so for example, if I say 3 squared equals 9, you could think of that in terms of log base 3. That says that sorry, log base 3 of 9 equals 2. Right? So that tells you about the power that you have to raise 3 to get 9. Right? If I say 7 cubed is 243, what is that as a logarithmic statement? Using log base 7. Amy? Log base 7, 243 equals 3, right? 7 cubed equals 243. Right? 2 to the 1/2, the square root of 2 is 1.4142 something something. This would say that 1/2 equals log base 2 of 1.4142, etc., etc. I mean, which is 2 to the 1/2, of course. Log base 2 of 2 to the 1/2 is 1/2. So we'll actually use that. Yeah, we'll use this observation shortly. Okay, but this is kind of a useful one, right? To every exponential statement corresponds a logarithmic statement. I'd say you want to mark that as something pretty important in this section. Right. So okay, let me just say one last thing. There's sort of an alternate viewpoint of, so yeah, okay. So there's kind of an alternate way of thinking about this, which is you can apply log to both sides. Okay, so you can change you can change the exponential statement to the logarithmic statement by applying the log to both sides. So let me show you what I mean by that. So here's the exponential statement. Here's the exponential statement. And let's apply log base 3 to both sides. Okay. What's log base 3 of 3 squared? What's log base 3 of 3 squared? Well, it's the power that you raise 3 to get 3 squared. What power do you raise 3 to get 3 squared? 2, right? So this is 2. And you notice that log base b of b to the n is just n, right? Because this is the power that you raise b to get b to the n. So that's just going to be n. So notice that power. Okay, right? And so applying log to both sides, you see that 2 equals log base 3 of n. That's this statement here, right? That's the logarithmic statement. Okay, so you can get from the exponential statement to the logarithmic statement, right? Same thing here, right? If I apply log to both sides, log base 7 of 7 cubed equals log base 7 of 243. Well, this is going to be 3. So it says 3 equals log base 7 of 243. That's the logarithmic version of that statement, right? And so you can go that way. And you can actually go backwards the other way by exponentiating from the logarithmic to the other. But we'll do that. We'll show that next time. Okay. Logarithms are kind of hard to get your head around at the beginning, so don't worry if it seems opaque at this point. It will come. See you.